He was the first professor here at UCSB that was an astronomer or planetary scientist. And he was someone that was a master at using physics to find out what was going on inside planets. Really the only solar system astronomer that we had here. And he was a beloved colleague that was interested in everything, and we all just enjoyed having him around so much. It was a huge loss. And we all got together afterwards, and we really wanted to just do something that would help us remember him. And we put together an endowment that many people in this room contributed to hold a special lecture in his honor every year or two. Two of those contributors are his family that's here. Priscilla and Doug are seated in the middle, and we're very happy to have them with us today. Our sixth Peale lecture today is going to be given by Katherine de Kleer, who like Stan, very much, I would say, is a master at using physics to find out about the dynamics of planets and to connect those dynamics inside, tidal effects and things, to what's going on the surface and in atmospheres. So it's a perfect match to the topic, I think. Katherine did her PhD at UC Berkeley and then was a 51 Peg Fellow at Caltech. And I guess they liked her so much they hired her as a faculty member. She's been there for 4 years now. I've got the story right. And I'm going to let you listen to her instead of me. She's going to tell us about the history of tidal heating at the Galilean moons.
All right, thank you very much. And is this at a good volume? Okay, great. Thank you so much for inviting me to give this lecture. I just want to say I didn't know Professor Peale, but it truly is an honor to give a lecture that is named after him. He did amazing work in my field. He wrote some of the foundational papers, and in fact, my work directly relates to 2 prediction papers that he published. One, a really classic paper, which I'll talk about in 1979, but also a 2002 paper. So my group works on a variety of different topics, but for a lecture in Stan Peale's honor, this seemed like the perfect topic to talk about. So what I will be talking about today is tidal heating in the Galilean moons, and very specifically in the moon Io. So that's what's shown here. That is the innermost of the 4 Galilean moons of Jupiter. It's the most volcanically active object in our solar system. And I will talk about how we are using Io's volcanoes to understand the process of heating by tides in its interior, and also the long-term history of the orbital dynamics of the 4 Galilean moons of Jupiter. So recognizing that this is a pretty broad audience, and that many of you don't think about planetary science very often, I will try to give all of the background. If I tell you something very basic, I don't mean to insult your intelligence, just want to make sure everybody is on the same page. And please feel free to interrupt me. I'm happy to answer questions, and especially if I use jargon or if something is unclear, happy to answer questions during the talk. So, the moons of our solar system are one of the main current frontiers of solar system exploration. The first set of missions that went out to the outer planets, Pioneer, the Voyagers, Galileo, Cassini, they were all focused on studying the planets themselves. But the data that we got back from those missions, pretty much everything that's shown here is images from spacecraft missions, have just shown us how diverse and unique each of the moons are. You can see they're all different colors. Some of them have atmospheres, some of them don't. They're also different from one another, and each one is an important data point for understanding how planetary systems as a whole form and evolve. And this is recognized by the current and next generation of spacecraft missions, which are targeting moons instead of planets. So the Dragonfly mission is going to Titan, the Europa Clipper mission, as well as Europe's JUICE mission, are going to look at Europa and Ganymede, and then our planetary decadal survey prioritized a mission to Enceladus to happen within the next decade or two. So this is a big frontier of exploration now is understanding these objects. This talk is going to focus specifically on the 4 Galilean moons of Jupiter, which we can get a lot of information about because they're so close, but they also are, they exhibit or a laboratory for understanding a very important heat source within moons as a whole, which is tidal heating, and I'll come back to that. But just to introduce these objects, going from closest to Jupiter outwards, Io, Europa, Ganymede, and Callisto, they represent this spectrum of geological activity, as well as the amount of heating that's occurring inside of them. So Io has a large amount of material heating, it's very volcanically active. Europa has these tectonic fissures on the surface and also has a high degree of heating, and then as you get farther out, they're a little bit colder and less active. This schematic shows cutouts of their interiors. So the outer 3 moons are what we call icy ocean worlds. They have crusts of water ice that's something like 10 to 100 kilometers thick. And underneath that, the 3 outer ones have global water oceans. Now, Io is completely different, and we're still trying to understand exactly why. I will answer some of that during the talk. Io doesn't have any water at all. It has a metallic core and some kind of mantle, but it's got quite a bit of magma, either in the form of a global magma ocean or kind of these interconnected melt layers. So Io's volcanism was only discovered in 1979. Prior to that, the only place in the solar system that we had confirmed had volcanic activity going on today is Earth itself. And this was discovered by the Voyager mission and was predicted just before the Voyager mission's arrival, as many of you in this room probably know, in this classic paper, Peale, Katherine, and Reynolds. This was published in Science, I knew it was either Science or Nature, but it said Science, just a few months before the first Voyager flyby of Io, and this predicted that due to the orbital dynamics between Io, Europa, and Ganymede, the authors predicted that there should be enough heating within the interior of Io in particular that part of its mantle should be melted, and that when the Voyager spacecrafts did their flybys of the Jupiter system, they would see evidence on Io's surface for this melting of the interior. So even before the actual direct detection of the volcanism, you could tell when we flew by Io, just from the imagery that came back, that something weird was going on there. So planetary surfaces are all cratered because they are exposed to space and stuff is hitting their surfaces. When you see a surface that is smooth, I know these might look like craters, but they're too irregular to be craters. So you can tell, kind of planetary scientists can tell by looking at these, they're not impact craters, they're something else. So the fact that you don't see impact craters on the surface immediately tells you that there's some sort of process going on that's filling in the craters or wiping out the craters in some way. So there's some kind of active process on the surface. And it was actually after Voyager flew by and was looking back at Io for the purpose of navigation. So this is a navigation team image that one of the navigation engineers, Linda Moravito, took this picture and was trying and saw, if you look in the upper left of Io, she said, oh, there's another moon in the background, and she tried to look up, according to her paper, what this other moon was, and there was no other moon there in the database, and it turns out that this is a volcanic plume off of the edge of Io. So, pretty fun way to make a discovery, and just amazing in that this was predicted by Peale, Katherine, and Reynolds, and with the prediction published just a few months before these images were taken. Just such a nice confirmation of a prediction that was made. So, briefly going through this heat mechanism that I'm sure you all are familiar with, but may not have thought about in a while. The heating of Io's interior, and the reason they were able to make this prediction, is that Io, Europa, and Ganymede, the 3 innermost of the Galilean moons, are in what's called an orbital resonance. This means that their orbital periods are integer multiples of one another. And the effect of that is that their mutual gravitational effects add up coherently instead of canceling out if they interacted at different points in the orbit every time. The effect of that is to pull their orbits from circular to elliptical. And then when you're in elliptical orbit, you are experiencing a changing gravitational field as you go around Jupiter. So the tidal effects are changing as it goes around. And that causes Io to be stretched out and compressed and stretched out and compressed as it goes around. A very exaggerated version of this is shown in the upper right. The actual mechanism for melting is that stretching of the shape, which occurs every 1.78 days, that's Io's orbital period, is generating enough friction in the mantle to actually melt the rock of the mantle, which is pretty incredible to conceptualize. So melted rock is just magma. This is the cause of the magma in Io's mantle, and then it comes out onto the surface in the form of volcanoes. This mechanism, while it is most active on Io, is actually present. It is, I would say, the primary heat source today for moons. So for planets in the solar system, like Earth is still heated about half from residual heat of formation, about half from decay of radioactive elements. But the ability of a planet to store those things depends on the surface to volume ratio. So moons, because they're small, they were able to radiate that heat away from formation. And the energy that is powering a lot of the change and interesting dynamics that we see on the surfaces and atmospheres of moons in the solar system has tidal heating as its primary heat source. So all of the moons that I've boxed in red here are currently in orbital resonances and have potential for tidal heating. Today, those that are boxed in blue have been shown by dynamical models to have passed through orbital resonances in the past. So this is not, a niche heating process specific to Io. It is occurring all across the solar system as well as in exoplanets. And Io, just because it is the place that this heating process occurs most prominently, is our best laboratory for understanding how it works. So the kind of basics of it is what I just explained, the interplay between the orbital dynamics and the dissipation and melting of the interior. But at the more detailed planetary interiors level, we don't actually understand how this process is working, which is largely arises from the fact that we don't well know material properties of these pressures and other conditions, compositions. So, for example, these four quadrants in the schematic show 4 different potential models for what that melting might look like. They largely differ in how deep within the interior the dissipation is occurring. So I guess I'll talk about all 3 of the upper left quadrant, probably everything except the magma sponge. So in the upper left quadrant, the dissipation is occurring near the core mantle boundary and the melt is propagating all the way through the mantle. In the lower left, the melting is occurring close to the surface. And in the upper right, it's also occurring close to the surface, but that is the magma ocean scenario, which there's some evidence for from the magnetic induction that's been observed when the Galileo spacecraft flew close to Io. There was a question.
Yeah, I have no idea what the relevant scales are, but is this dissipating gravitational potential over time? Does that make sense as a question?
I'm not sure.
The only source is Ganymede's potential and gravitational potential.
Yeah, so you do have a trade-off. So there's dissipation that is occurring both in Jupiter and in Io as the orbit, and the orbit is attempting to circularize, but is unable to circularize because of the gravitational effects of Ganymede.
But they're driven outward. How are they driven out? They're going out.
Sorry?
They're going outward, right? Like iron.
Are they moving outwards overall? That is a question, what the overall migration of them is. And some of the dynamical models show them actually moving in and out of resonance. So when they are deeply in resonance, you have a large amount of dissipation. When you have enough dissipation, you actually melt the interior enough that it's liquid and therefore no longer dissipative. And then it will move out of resonance towards circularization.
Well, in the case of the Earth and Moon, isn't the energy source the Earth's rotation? Because the Moon is moving out.
Yes, because you have the tidal bulge that is raised on both the Earth and the Moon. It depends on the rotation rate of the planet is almost always faster than the orbital rate of the moon.
So I guess I had guessed that this would have been an expense of Jupiter's rotation, but I don't know.
Yes, I think the like bulk outward expansion of the orbit is somehow complicated by the resonance. So when we actually observe astrometrically the evolution of the moon, some of them seem to be moving inward and some of them seem to be moving outward. So it's not clear that there's an analogous situation, which I believe comes from the resonance, but I've not actually worked through that physics myself.
Okay.
Yeah. Yes.
So on Earth, the tidal energy is dissipated by the oceans. Is that right, or is that not really right?
So on Earth, you have the tidal bulge that is
Right.
raised on the Earth by the moon. Because we have a liquid layer that is unbounded by a shell, you're able to move the ocean up and down by a relatively large amount. So you do have tides that are raised on Jupiter by Io and vice versa. The same between the Earth and the moon. I mean, the Earth is raising tides on the moon.
Sure.
It's solid and the effect is small.
No, but so I'm just thinking, what's the analogy between where the energy is dissipated on the Earth versus where the energy is dissipated in Io? I mean, you're raising a tidal bulge in both cases, but I'm having trouble making an analogy for where I should expect the energy to be dissipated and why.
In the interior,
Yeah.
I mean, the reason that we have these different scenarios that we don't know the answer to is because it's not obvious where the dissipation should be occurring. It depends on the stress-strain relation for the materials that we're looking at as a function of depth within the interior, so therefore as a function of temperature and pressure. And it's not a priori obvious whether it's the materials at the core boundary or in the shallow surface that should be the most dissipative. Yes?
You have quite a detailed picture of the structure.
Yeah.
And at least the relative sizes of everything. How was all of that determined?
You mean here?
Yes.
Well, this is just a schematic. I don't worry too much about the relative sizes of things in the schematic. The core radius, we don't know to within a factor of 2. The width of the magma ocean here is very much exaggerated. But basically, the size of the core compared to the size of the mantle is determined from the moment of inertia based on gravity measurements. The thickness of the crust is determined based on the tallest mountains. So you calculate the thickness of crust that can support the mountains. Okay, I better get back to the topic now. And hopefully I'll answer some of the questions that people have as we go along as well. So we want to understand what's happening in the interior, but we don't have access to the interior. So one of the ways it turns out that we can distinguish between these different scenarios is by looking at where the heat is coming out on the surface. And this kind of makes sense. I like to give an Earth analogy. If you look at where the volcanoes are distributed across Earth, which are all shown by the little red markings here, you of course learn something about Earth's interior. You learn that we have tectonic plates. You more or less learn where their boundaries are. So Io does not have plate tectonics as far as we can tell, but where the volcanoes are in the surface still differ for these different models. So these maps are showing the asthenosphere is just that shallow heating layer that I was talking about before. So under these 3 different scenarios, yellow is the latitudes and longitudes where more heat should be coming out, and blue where less heat should be coming out, and hence where we expect the volcanoes to be distributed under these different scenarios. So just to briefly talk about how these models are done, you basically break Io up into a bunch of spherically symmetric shells. The dissipation within each shell is the sum of spherical harmonic terms, primarily degrees 2 and 4 are represented. And then you just integrate the heat radially outwards under the assumption that there's not lateral heat flow. The magma ocean case is the one case I'm showing that deviates from that, where you actually do have some lateral transport of heat. So these models differ from one another, both in which longitudes you expect the volcanoes to be at, but also as you can see pretty strikingly between the two on the left, whether you should have more heat in polar regions or almost no heat in polar regions. So by looking at where the volcanoes are occurring on the surface, we hope to understand what the interior of Io is doing. But we can't just take one snapshot and understand how the volcanoes are distributed. We actually need a statistically meaningful sample of these. So this is one of the things that my group has been doing for actually almost 10 years now, maybe 10 years now. So we've been monitoring the volcanoes on Io using telescopes on top of Mauna Kea, primarily the Keck telescopes. So this is an image of what Io looks like from Keck. You see reflected sunlight off of most of the surface, but the little bright spots that you see are thermal emission that's coming off of the volcanoes, because these are at a near infrared wavelength. So you can see that we can resolve several volcanoes from one another. We can sort of see how bright they are and look at them over time. And just kind of as a fun side note, I really appreciate getting to observe volcanoes on Io from the top of the volcano. And occasionally, when we go out there, the volcano is active, but not actively disrupting our observations, which is bad. And we actually get to image both on the same night. And some of Io's volcanoes actually are lava lakes that are analogous to this one, just a lot bigger. So some of these spots you see on Io are probably lava lakes on Io, which is pretty cool. So we've taken snapshot observations of Io like these on something like 400 nights now. The observations only take 20 minutes, so this is not like 400 nights of telescope time, it's just 400 snapshots. This is a now relatively small sampling of the observations, just so you can see how different they look. It's roughly sorted by increasing wavelengths, so at the top is the 2 micron data where you mostly see reflected sunlight. At the bottom is the 5 micron data where you can just see how much better the volcanoes stand out against the disk of Io. So from each of these images, we identify the latitude and longitude of the volcano and how bright it is. We do this in multiple filters, as you can see, and then you can get a constraint on the temperature and the total thermal power coming out of that volcano. And we can look at how these things are changing over time.
Do you use adaptive optics?
Oh, yes. So these absolutely use adaptive optics. Io is about 1 arcsecond in angular size, and so without adaptive optics, it wouldn't be resolved at all. All of this is enabled by
Is it sort of
AO.
self-calibrated, or do you use a laser offset?
So Io is bright enough. The adaptive optics use the optical light, or at least this system does.
Right.
So Io is
its own self-calibrated.
it's like 6th magnitude, and it is definitely bright enough to do National Guide Star adaptive optics. Yeah, it's perfect. It's very easy. If we had to use the laser, we wouldn't have gotten 400 observations. Yeah.
The laser spot's bigger. The laser spot is bigger than Io too. It's
Oh,
like-
really?
yeah.
Okay, I have never actually
It's
used the laser
a couple
sensor.
of seconds, I think.
Okay. So this animation is now just showing, pulling out the brightness of each of these volcanoes over time. It'll cycle around. It's about the first kind of half of our data set is captured in this animation. So we've been tracking about 100 volcanoes on Io now over the past 10 years. You can see by that some of them exhibit different geological characteristics just by looking at this. Like the one under 30-degree longitude is always pretty much putting out the same amount of energy, but if you look at the one at the 300-degree longitude, that one is actually periodic. And we wrote a paper speculating or hypothesizing that the periodicity is actually due to periodic oscillations of Io's orbital eccentricity over like a 1.5-year time scale. So the orbit itself is oscillating as well. And I could spend plenty of time talking about the geology of any of these volcanoes, but I will not do that within the context of this talk. Since we're talking about looking at the global properties, so if I stack together all of these observations, this is kind of what that distribution looks like. And maybe to first glance, this looks relatively random, but you actually can see some signals of the distribution of the volcanoes. For example, you see that they're roughly clustered into what we call the leading and trailing hemispheres. In this, it's the right and left hemisphere. So Io is tidally locked, so the leading hemisphere is like the front one in its orbit, and the trailing is the back hemisphere. So they're roughly clustered into the 2 hemispheres. You can also see that there are two distinct kind of longitude bands on the trailing or left hemisphere that have specific separation, and that separation is actually consistent with the separation in the degree 4 spherical harmonic term, and then of course the clustering of the two hemispheres is consistent with the degree 2 term. So we are seeing distributions that are kind of consistent with the two models, and I'll come back to showing those models so I can show you that it's actually not a great comparison, but we at least see some features of the distribution that are consistent with where we expect the heat deposition to be occurring. I see there's a question in the back.
Which side is Jupiter on?
So Jupiter is at longitude 0. Longitude 0 is facing Jupiter, longitude 180 is facing away.
And could you describe a little more? The two hemispheres is so different. It's remarkable. I mean, you know.
So there is a difference between these two hemispheres it's actually not in the total amount of heat flow that's coming out, it's in the style of the volcanoes, and we do not understand where that's coming from. In terms of tidal heating, the leading and trailing hemispheres should be symmetric. The sub and anti-Jovian are not perfectly symmetric. To first order, they're symmetric, but if you add one more term in the Taylor expansion, it's like an 8 or 10% difference actually between the sub and anti-Jovian. But these two hemispheres should be symmetric, and I have some kind of wild ideas that are not well developed on why we might have differences between these two hemispheres, which have to do with the fact that the plasma at Jupiter's magnetosphere is impacting one hemisphere, not the other. But yeah, we don't have an explanation for that at this point. And this effect is also seen if you add the Galileo data set. So this is a figure that I put together for a recent book chapter that includes a much larger data set. So this is AO now over a 15-year time period, AO being the ground-based adaptive optics observations. And then the Galileo spacecraft data on the bottom, and you can see some of the large-scale features, including the asymmetry between the two hemispheres, show up in both data sets. So we see some of this evidence for, like I said, degree 2 and degree 4 terms, but to compare that with those predictions, and I'm sorry, the color scale is different now on my tidal heating models, but they are basically the same three models I was showing you before, with now the locations of the volcanoes overplotted. You can see that none of them is a particularly good fit at this point, largely because of the fact that the two hemispheres aren't the same. So the magma ocean model kind of looks like it fits in the leading hemisphere on the right, but it like anti-fits on the trailing hemisphere on the left. What I kind of think is going on is that we have overall a better fit to these shallow heating models than for the deep heating models, but the fact that we have those large volcanoes that are occurring at high latitudes, I think means that the polar volcanoes are being sourced from deeper in the mantle, that the heating is occurring more at the core mantle boundary. Those volcanoes near the poles are more energetic and they're hotter, but there's not overall more heat flow. So a small fraction of the heat flow is being sourced from there, but it is producing the most violent volcanoes. Whereas the shallow ones are producing, is more of the dissipation overall is coming from shallow, but is producing these kind of more low level but persistently active volcanoes.
I was going to ask when, could you remind us when the Jupiter mission was?
The Galileo mission
mission.
Was from the mid-90s to the early 2000s. I don't remember the exact date.
So that predates basically the lower image is earlier than the upper image.
Yeah, it almost exactly predates. I think it ended, or at least wasn't returning usable data after something like 2003.
Okay.
Yeah. Okay. So So we think we have kind of a picture for what's going on here, and as was pointed out, we now have data going back to, well, going all the way back to 1979 of Iowa's volcanoes, and so we have almost a 45-year timeline of Iowa's volcanic activity, which is pretty exciting, and we're continuing to build up this statistical data set, but ultimately 45 years is not very much in geological time. And the questions that I'm interested in, beyond these questions of Io's interior, have to do with the history and the very long-term history. So I'm now going to kind of transition to talking about a different project also related to Io that has to do with not a 45-year history, but a 4.5 billion year history. So I've gotten very interested in these two questions here. How long has the Laplace resonance, which is that 4-2-1 resonance between Ganymede, Europa, and Io, existed? And why does Io look so different from the rest? So you look at these cutouts, 3 of them are ocean worlds, and then Io is just this outlier. Did that happen because it formed close to Jupiter, where it was just too hot for ice to condense, and ice was never somehow delivered to it? Or was it once basically Ganymede, and it lost its ocean and ice shell over time because of tidal heating and then loss of the hydrogen? So now I come to the second prediction that Professor Stanton made. This is Peale and Lee, 2002, and this was the first prediction that the Laplace resonance between these satellites was primordial, that it happened in the first 10 to the 5 years of the formation of the solar system, which is very, very fast on geological or astronomical timescales, of course. So this prediction has been borne out in more recent numerical models, not proven observationally, but here's an example of I think, the most recent paper that has made the same prediction, Peale and Morbidelli in 2020. Interestingly, these two papers have a very different mechanism. In the Peale and Lee paper, the Galilean satellites form closer to Jupiter and migrate outwards, and they're captured into resonance as they migrate outwards. In the Peale and Morbidelli paper, they form farther out and migrate inwards, and they're captured into resonance during the inward migration. But the time scales are like 10 to the 5 for this one and 10 to the 4 for this one. So in either scenario, you capture almost immediately into resonance. So formation models show that this should potentially be the case, that they've been in this resonance, and hence that Io could have been experiencing this level of volcanic activity for 4.5 billion years. So we'd like to be able to get observational evidence for that. The problem is, this picture I showed you before tells you that we do not have a long record of Io's history. Io has no observed impact craters, even at the highest resolution observations, and that tells us that its surface should be hold a record of no more than the past million years. So how can we answer the question of whether Io has been volcanically active for 4 billion years? I think that we can do that using isotope geochemistry. So this may be another topic that people have not thought about for a long time, so I will introduce it a bit. So specifically, we're going to be talking about sulfur isotopes. Sulfur has 4 stable isotopes. We're now not talking about things that decay radioactively. These are stable isotopes. So the main isotope of sulfur is sulfur 32, but you also have naturally occurring 33, 34, and 36. The main one I'll be talking about today is 34, and that's because the 32 sulfur, kind of regular sulfur, is about 95% of sulfur in the solar system. The 34 sulfur is about 5% of sulfur in the solar system, and the other two are very small amounts, small enough that they would be hard to observe from Earth. And what is really useful about isotopes is that they are not affected by most processes. So the impact cratering of the volcanoes, they're not going to have a large effect on the isotopic signature, but what will have a large effect is, I'll put it this way, a small effect compounded over a very long period of time. So I kind of am showing that in the schematic here. We think that Io's sulfur cycle, another graphic for this here, consists of the SO2, which is the main molecule that is holding the sulfur, being outgassed from the volcanoes into the atmosphere. Once it's in the atmosphere, some of it is lost to space. Actually, it's lost to space at a rate of 1 or 2 tons per second. It's a pretty high mass loss rate. What's left behind in the atmosphere freezes out onto the surface. Much of it freezes out onto the surface. And then it gets overlain by plume deposits or lava flows. Believe it or not, the lava flows don't completely sublimate the SO2 ice. You can think of it like a lava flow over a glacier in Iceland. It's hot, it sublimates some ice, but it doesn't come anywhere close to melting the entire glacier. So the sulfur gets recycled back again into the interior, gets reincorporated into the magma, and then eventually outgasses again into the atmosphere. So it's kind of interesting. You can do a back-of-the-envelope calculation for at Io's resurfacing rate. So the rate at which stuff gets deposited globally on a surface, it's about 1 millimeter to a centimeter per year. If you multiply that out over 4.5 billion years, you get that Io's entire mantle has to have come out onto its surface in the form of volcanoes and been recycled tens to hundreds of times. So all of the sulfur in this whole system has potentially passed through the atmosphere tens of hundreds of times. When it passes through the atmosphere, some of it is lost and some of it is recycled. So you have this compounding system, and you're preferentially losing the lighter isotope. That happens fairly intuitively. You can set up a gravitationally stratified atmosphere on just a couple of hour timescale because it's so thin, just due to molecular diffusion. And so the stuff that's being lost, which is mostly coming from the upper atmosphere, is preferentially the lighter stuff. So when this occurs, if this occurs just once, it doesn't have a large effect, but when you're doing this over and over and over again, over 4.5 billion years, you could potentially build up a very heavy reservoir of sulfur, meaning that there's a lot more 34 sulfur relative to 32 than Io started with. So we have built a model for this. Actually, my former postdoc, Ari Hughes, who is in fact an earth volcanologist, so she knows what she's talking about when we are talking about geochemical modeling of volcanoes. And I'm not going to talk anything about this model except to say that I'm presenting this in a very simple schematic way, but the model actually does have a lot of different terms for how sulfur is exchanged between reservoirs and how all of these processes affect the sulfur isotopes. But the kind of simplified version of the model is this. We assume some initial composition for Io, and we have good bases for assuming all these things. I'm happy to answer questions about it, though, if people want to know where we get our guesses from. We then differentiate Io into its mantle and core. The sulfur that goes into the core is stuck there forever. It doesn't come back out into the mantle, at least in our model. And then we have this kind of outgassing and recycling, as well as escape. So the model can predict how the heaviness of the total sulfur reservoir is changing over time. And I'm going to try to do this without needing you to understand isotope geochemistry units. I think they're added on here. If you want to understand them, this unit is a parts per thousand difference between something and the standard for that thing, where the standard is a specific mineral, iron sulfide, within a specific meteorite, the Canyon Diablo meteorite. So this is where the standards come from in geochemistry. But basically, up is always a heavier reservoir, down is always a lighter reservoir, so if you don't want to worry about the units, just remember that. So the model shows how the mantle and crust get heavier over time as the lighter stuff is lost. So this is time over 4.5 billion years running this numerical model, and we can change the conditions. We can change how much melting there's been over time. We can change how much mass loss there's been and kind of see what we expect the sulfur isotopes to look like today under these different scenarios. And then we can go observe the sulfur isotopes. So this is possible at millimeter wavelengths using ULMA. ULMA is a radio interferometer working at millimeter and sub-millimeter wavelengths. It has extremely good sensitivity and has very good spectral resolution. So what we're looking at is rotational emission from rotational transitions of the molecules. And if you replace the 32 sulfur with the 34 sulfur, the rotational transition is actually shifted quite a lot in frequency relative to the spectral resolution of ULMA. So this is what images of Io look like in a variety of these emission lines. And so in each of these little snapshots, one of these is the leading hemisphere and one of them is the trailing. So that's why you can see the sub and anti-Jovian swaps between the two. The dotted circle is the size of Io. You can't see it because I've subtracted off the thermal emission from the disk. So what you're seeing is on Io the distribution of each of these gases across its surface. So for example, if you look at the SO2 down here, basically the SO2 atmosphere is distributed fairly uniformly at low to mid latitudes. That's where we see the emission coming from. It looks like there are these bright spots towards the edges, but that's just because the gas is thin, and so you're just seeing a longer column of gas. You're seeing emission from a longer column of gas towards the edges. So it's fairly uniform at the low latitudes. So we've detected the 32 and 34 sulfur in both sulfur dioxide and sulfur monoxide. We also have been looking at the chlorine isotopes, mainly because they are easy to detect. So this is NaCl and KCl gas, and they, for both the 35 chlorine and 37 chlorine, I won't talk too much about chlorine in this talk. We do not have a good understanding of what Io's chlorine sulfur looks like compared to the sulfur cycle. So it's a bit harder to interpret. But the NaCl and KCl gas you see do not form this like low latitude band. You see them in distinct volcanic plumes is what we think they are. So these are hot alkali gases. The gas temperatures, the rotational temperatures are something like 800 Kelvin. So we think that these are hot volcanic gases coming out of the plumes. This is what the spectra look like, at least for the sulfur-bearing molecules. They're centered on each of these lines. These are all around 430 gigahertz, which is in the submillimeter. And you can see that we get quite good signal to noise on these emission lines. The model that's overplotted here is a radiative transfer model where we have some column of gas and basically propagate the emission and absorption that you see going through the atmosphere. You can see that the model gets a fairly good match to the data. The wings are not well captured, which could be due to winds in Io's atmosphere. And we're actually working now on trying to make a wind map for Io's atmosphere to see whether it has like day to night winds or low latitude to pole winds. It's kind of a separate, interesting atmospheric dynamics problem. But in terms of the main purpose of doing this modeling is that it allows us to get the densities of the gases in Io's atmosphere to look at the ratios between the 34 and 32 sulfur in the sulfur dioxide. And this number, which unless we have any geochemists in the room probably won't mean anything to anyone, is the value that we get for how heavy the reservoir is. And basically what this is saying is that it's 36% heavier than the standard. But what does that mean? Is that a big number? Is that a small number? Using the scenario that I talked about where you have this recycling and incremental loss over time, this is a process that's known as Rayleigh distillation. And under that process, you can relate this number to the amount of sulfur that has been lost over the entire history of the system. It's quite a simple equation. You need to know the starting sulfur isotope ratio, the 34 to 32 sulfur. You need to know how light the material that's lost is compared to what's left behind, and then you can turn your measurement into this F, the value we're very interested in. That's the fraction of the original inventory that still remains today. And if we make that conversion from our measurements, we get that Io has lost 94 to 99% of the sulfur that it started with, or at least the sulfur that's participating in this recycling and loss process. So is that actually a lot or is that not a lot? Obviously, it seems like a lot, but how does that compare to kind of a back of the envelope calculation based on, for example, Io's current mass loss rate propagated back through 4 billion years? So this is my kind of back of the envelope calculation on a slide. Assume that Io formed with typical solar system abundance of sulfur, which we get from meteorites that we think are representative of the solar nebula. That means Io was originally about 2% by mass. That gives us a number of kilograms of sulfur. And we assume it has the typical sulfur isotope ratio, which I'm happy to talk more about at the end if people have questions about that. But some fraction of the sulfur is in the core. The core is made of iron and iron sulfide, and we don't exactly know how much of each. But if we take the constraints from Io's moment of inertia and also how much sulfur should partition into the core versus mantle, assuming that Io solidified in equilibrium, then that tells us that 80 to 97% of that initial 2% sulfur that Io started with should be locked in the core. So we have only the 3 to 20% of that sulfur available to participate in that process. And then we're also going to assume that all sulfur loss has, for simplicity, has occurred in the form of sulfur dioxide like it is today. What you then get, taking all of these numbers, is that Io has been losing mass on average at basically its current rate, plus or minus, so from half to 5 times its current rate over the entire history of the solar system. So it actually kind of fits together nicely that the 94 to 99% is pretty close actually to the amount of sulfur if Io has been losing mass at its current rate over this whole time period. And what that means is that Io has been essentially volcanically active for, I can't say exactly the entire age of the solar system, this is kind of to within a factor of a few, but that it's been volcanically active and losing mass at least 4 billions of years, assuming that its mass loss rate today is representative of its history. And potentially it has to have even been losing mass and hence more active in the past than it is today. So while we have a kind of uncertainty of a couple billion years, so I can't exactly say that the Laplace resonance is primordial, this certainly supports it. I would say confirms an ancient origin for the Laplace resonance, because of course Io would not be volcanically active if it weren't in this resonance, and it's consistent with or supports the primordial origin as was originally predicted. Just to compare this, to further convince you that this is a really big number, the heavy sulfur isotope ratio, the 36%, this is how that measurement compares to other objects in the solar system, as well as a few extrasolar things that I could find data points for in the literature. Earth, Moon, Mars, OCs, ordinary chondrite meteorites, and out here are some comets in the ISM. So Io really does stand out in having an anomalously heavy sulfur inventory. It makes sense since it's losing 1 to 2 tons per second of primarily SO2 that this would be the case. I think it all kind of hangs together as a nice story, but it really does stand out. As well, the chlorine isotope is also anomalously heavy, although as I said, we have a much poorer understanding of what the chlorine cycle might look like, but that's something that we're starting to think about now. Okay, so just to bring this back and wrap up here, we are using Io's volcanoes to learn about its interior as well as the history of tidal heating, which reflects on the history of the interiors of the other moons that are in this resonance, and ultimately to try to use Io as a laboratory for understanding this important planetary heat source that we can then apply to a better understanding of how solar system moons evolve in general and answer these interesting comparative planetology questions about how each of these moons came to be the way it is and why it doesn't look like any of the others. I'll wrap up there and happy to answer more questions. Okay, lots of questions.
What's the answer about the history of water on Io?
Oh yeah, I brought up the question of the history of water on Io. So we don't have an answer to that question, but now that we have the measurement for the sulfur isotopes, I think that we can answer that question, because if you assume that all of that loss, that all the loss from Io forever has taken place in the form of SO2 only and not water, then based on the sulfur isotope ratio, that predicts an oxygen isotope ratio. However, if you have lost a lot of sulfur in the form of water, then the oxygen isotope ratio should be heavier than the sulfur one predicts. So
Is that what you meant to say, or did you mean losing oxygen? So
yeah, maybe I mixed up my wording. So under the assumption that all of the loss has taken place as SO2, meaning if I have never had water and all the loss has always been in SO2, then the sulfur isotope ratio that we measured predicts an oxygen isotope ratio. However, if Io once had an ocean of water, including all the oxygen in that water, and lost its ocean of water, then the oxygen that was left behind by that should be quite heavy, even heavier than is predicted by our sulfur measurement. So I think by measuring the oxygen isotope ratio, we can get at whether Io once lost an ocean of water. This is, by the way, for people who aren't aware, how we think that Venus once looked like Earth, that it once had an ocean, and exactly this is the argument for the fact that Venus once had an ocean. It was the D to H ratio in water instead of the oxygen ratio. I'd love to measure the D to H ratio on Io, but first we have to find some H. Okay.
Could you just say a little bit about this bulk composition? So at the surface, what's the dominant element in the atmosphere?
Yeah, sure. So the surface is sulfur and silicate. The lava flows are broadly silicate. They're probably more or less basaltic, like on Earth. And then the surface is coated with sulfur dioxide frost that froze out onto the surface. And then there's a sublimation-supported atmosphere. So the temperatures at Io's surface are very, very close to the freezing or alternatively the sublimation point of SO2. So it exists in both solid and gas form.
So there is a stable hydrostatic atmosphere or not?
During the daytime, there is. And then at night it freezes out because, like I said, we're very close to the freezing point of SO2.
So has somebody looked at just high energy particles from Jupiter doing spallation to make the other isotopes you're talking about? Given that there's no column to protect it, high energy particles would spall. And your elements your element is more abundant, is more massive, so spallation.
Yeah, so the high energy particles, the ionized particles don't reach to the surface, and that is because Io has an ionosphere, so the ionized particles probably don't get closer than a few hundred kilometers above the surface because they're diverted around Io. The loss processes are almost all interactions between the high energy particles and molecules in Jupiter's atmosphere. So my complicated model schematic I showed had like 6 different loss processes. Almost all of them are interactions between high energy particles in Jupiter's magnetosphere and molecules in Io's atmosphere. Yeah. Max had a question.
Can you talk about what we've learned from Juno about Io?
Yeah. So Juno, in its extended mission, is observing the satellites. Its first close approach of Io is going to occur in December of this year, and then it has another close approach in February. So it has taken some distant measurements of Io for sure. There are really nice images of its hotspots. And in terms of, there's actually a nice connection between Juno data and what I talked about today, specifically in the tidal heating models and how the models predict different polar heat flow in the 2 different scenarios. So Juno is on a polar orbit, so for the first time we've got a good view of the polar regions. And there was a paper that was published just a few weeks ago that's the first thermal emission map of Io's poles from the Juno spacecraft. And it shows that there is an anomalously low heat flow coming from the poles. So that supports that shallow heating model. And I expect when we actually get the close flybys, there's going to be some really awesome data that comes down from that. I think Tim had the next hand raised.
Can you measure the uniformity of these isotope ratios over the surface, and would that tell you something about the long-term intensity of volcanism in different latitudes, or is it too hard to measure? Is the atmosphere going to mix too thoroughly for it to be a useful measurement?
Yeah, it's a good question, and our referee asked me that too, so I actually did that. So if you look at this graphic, basically what I did was measure the isotope ratio in each of these plumes that you see here, as well as in the SO2 ones, in the 2 bright blobs and then in the center of the disk. And the uncertainties are pretty high, and I did not measure a statistically significant difference between any of the regions on the surface. What I think would be really interesting to do is look at the difference between the sulfur isotopes in the frost versus in the atmosphere. There are predictions for what that difference should be based on what's called a vapor pressure isotope effect, just how the isotopes should partition between the two different phases of matter. And actually there's someone who is working on making the measurements in the lab at Caltech of what that isotope effect should be at IO-relevant conditions. Yeah, so I think that there is certainly, in terms of looking at different like bulk reservoirs, something interesting that you can learn, and we'd like to do that for sure. But okay.
These would be incredible targets for the BLT interferometers.
Sorry?
These would be incredible targets for the BLT interferometers.
Yeah.
Have they been observed that are there, two wonderful IR interferometers for the near and mid IR on the 4 BLT elements?
Yeah, so let's see. We have at least proposed and been unsuccessful at getting VLTI observations of IO. I have made LBTI observations of IO, and so we have the interferometry at, let's see, 5 microns and also at 10 micron imagery from LBTI, but I agree that extending that to VLTI would be fantastic.
Fantastic. You get real images, but it's amazing instrumentation.
Okay, well, we'll keep proposing. What instrument do you have in mind?
These sources are not too big because they're volcanoes. No, I mean, to me, volcanoes is not high.
Some of the volcanoes are as big as 100 milliards seconds. So
Yeah,
there's potential to actually resolve
but
them.
I would be that's volcanoes.
Right, yeah. Yeah, okay.
In looking at your movies of the time variation of the plumes, can you conclude anything about the plasticity of the surface and the subregions from evidence of plumes that do not reappear? I realize you'll look at a data set, but on Earth, typically volcanoes come from the same place over long periods of time. They erupt, they stop, they erupt. Can you tell anything like that from the data you have?
You mean whether we are seeing the reappearance and shutting off of new volcanoes? So the high-resolution spacecraft imagery tells us where the volcanic surface features are. So we can see the patera, caldera, whatever, and fissures and things. And those give us a roughly 1 million year record of the volcanism. So when we see thermal emission in a new spot, almost all of the time, we can look at the high-resolution imagery and see that there was a geological feature there. There have been a couple notable cases where some of those volcanoes that showed up consistently in my movie do not have a corresponding surface feature in Galileo data. So that is something that's going to be cool about the Juno data set. For these volcanoes that have newly appeared since we last had high-resolution imagery, it will be really, really interesting to see whether we have some big new volcano, some new fissure, like what do those regions that are newly volcanically active look like? Oh, there was a question over here that maybe wasn't asked first. Okay.
How sensitive is your sulfur isotope story to other assumptions about, say, sulfur moving from the core, from diffusion of sulfur from the core?
Yeah, so
that seems to be like a big assumption that you're making.
Yes, and the petrologists tell me that it's a very reasonable assumption, but it does not affect our interpretation in the sense that if you have all that sulfur locked away in the core, that is not participating in the recycling and loss process. If you're leaching sulfur from the core into the mantle, it's a low rate, one directional flow, and you are basically just injecting something at the initial isotope ratio into this system. So you're making the system slightly lighter than it otherwise
So it's
would
going
be.
to change your timescale, so.
It would change, it would make the scenario that we needed to match our observed isotope ratio even more extreme in terms of Io's past mass loss rate. So we basically decided that leaving the silver locked in the core is the conservative assumption, because if a little bit of it is coming into the system, it just makes our interpretation a little bit more extreme. So I think our qualitative conclusions at least are robust to that. Yeah.
So I'm wondering if we can get a final question from a graduate student.
First, great talk here. So the volcanic activity data is over the last 40, 50 years, but you mentioned you also have surface features to look at.
Yes.
If you look at the distribution of those, do they coincide better with one of the three models that you showed?
So the distribution of the surface features, the Peale, show, actually they correspond pretty well. It primarily shows two peaks, just like the volcanoes do in the leading and trailing hemisphere. And in addition, even in the trailing hemisphere, you see that kind of double peaked at the, whatever it was, like 210 and 240 longitudes or something. There is potentially a longitudinal shift between the volcanoes and the Peale, which I don't know if that's statistically robust. It's a little bit strange when you plot the histograms side by side, they're offset by something like 15 degrees. But
at least in terms of, say, the latitude distribution, the two, where the dissipation is at the lower level versus the higher level, there is a clear absence of the poles or presence of the poles of these features. What do you see in the surface features?
the imagery in the polar regions currently is really poor. It's easier to see thermal emission from that high angle than it is to actually map the Peale. The imager on the Juno mission does have this data, and people are working on updating the geological maps, and the data sets will get even better, but we already do have the first imagery of the Peale in the polar regions, and I'm sure that people, including the student in my group, are going to be working on this analysis to try to see what that distribution looks like of the Peale. Because you're right, it gives us about a 1 million year record, so kind of intermediate between the 45 years of the thermal emission and the 4 billion years of the isotopes.